Hello. Today we're starting off the rest of the chapter, which is all about isotopes. And a learning objective 4.3.2 is explaining how isotopes are different from each other. And in our previous videos, we have shown that isotopes are different from each other in that they have different number of neutrons, but they are similar to each other in that if they are isotopes of the same element, they would all have the same number of protons. So looking at the graphic that you have here, you can see these are three different isotopes of neon. They're all definitely the element neon because they all have 10 protons in its nucleus. And since they are atoms of neon, which means that they are electrically neutral, they have the same number of positive protons as negative electrons. But how they differ from each other is the number of neutrons. And what that is going to have an effect on is the mass number of the different isotopes. Remember, the mass number is the number of protons plus neutrons. So this example of neon would have a mass number of 20, and you can see this is how we're going to designate what particular isotope we're talking about. We have the element's name dash its mass number. That's something that's called isotope notation, and an isotope notation can just be a way to identify which isotope of an element you are referring to. And there's two main ways that we have isotope notation. One way is by writing the name of the element and then dash its mass number. Or we can have the symbol of the element, then the top number is the mass number, and the bottom number is the atomic number. This is sometimes difficult to type out, so sometimes you'll even just see it as this, or I guess that would be not chlorine 17, but chlorine 35, just without the atomic number in the lower left hand corner. The placement of these numbers is really important because in every corner of the symbol, those numbers mean something different. A number in the upper right hand corner is going to mean the charge, that it's an ion, and the number in the bottom right hand corner means how many of that element you have. And we're going to move on to talking about that number that we see on the periodic table, the average atomic mass. That's our last learning objective for this chapter. So the first thing that we need to review, we've looked at this earlier in the chapter, but what is this atomic mass unit? Well, it is literally the unit used to mass atoms. So hence it's very small. And how they define it is 1/12 the mass of a carbon 12 atom. So basically it is the average mass of a proton and a neutron. And a proton and a neutron weigh very similar masses, but not completely exactly the same. So therefore, an atomic mass unit is not exactly equal to the mass of a proton or an electron, or a proton or a neutron. It is sort of the average of the two. It's very, very, very small, and the reason why we use this instead of grams or even a nanogram or a picogram, those would be even, a billion times smaller than a gram. It still would be way too large to talk about the mass of a proton or a neutron or an electron. So if we look at this table here, we will see a listing of some of the common earlier elements, the different isotopes that there are of those elements in nature, something we're going to call the relative abundance, each isotope's mass with the unit of AMU, and then its average atomic mass. I'm just going to write average over this. Sometimes people just call it atomic mass, but I like really referring it to average atomic mass just to hit home that it is the mass of the average of all of the isotopes. So if you look at an easier or a good atom to begin this with is actually chlorine. And the reason why I like to start talking about chlorine is because their percentages are relatively large. There's one isotope of chlorine, chlorine 37, that's about 24% of all the isotopes of chlorine in the world have 17 protons but 20 neutrons. So its mass number is 37. And you can see, even though we say that an AMU is about the mass of a proton and an electron, you can see that the mass of that particular that particular isotope of chlorine is about 36.966. And then if we take the other isotope, chlorine 35, that has 18 neutrons in it, its mass is a lot smaller, about 35.96. The average atomic mass of those two, though, is 35.4. It's not exactly right in the middle. What's right in the middle of 35.9 and 34.9 and 36.9 would be 35.9. So it's not the absolute average. You don't add them up and divide by 2. You need to take into account the fact that, well, most of the atoms of chlorine in this world are chlorine 35. So that's why the mass is the average atomic mass is a little bit lower than what it would be directly in the middle. But in the end of the day, if we have a sample of salt and half the ions of salt are made of chlorine, we don't know whether there's more chlorine 35 or chlorine 37. What we found is that the natural abundance is pretty universal. So that salt taken from the Dead Sea has about 75% chlorine 35, but salt that you will find in Peru will also have about 75% chlorine 35. So we can use these percent abundances to figure out the average atomic mass, and then the average atomic mass is what we can use anytime we need to talk about the mass of the atom. So when we discuss the definition of average atomic mass, we want to make sure that we really highlight the fact that it is a weighted average. So it's the weighted average mass of all the isotopes that exist in nature. And now let's take a look at some of the other elements. If you look at carbon here, almost every isotope of carbon almost every atom of carbon that there is in the world is carbon 12. Carbon 12 makes up 98.89% of all the carbon atoms out there. But some carbon atoms, about 1% of them, are actually carbon 13. So therefore, if I have a sample of carbon, notice that the average atomic mass isn't 12.000, it's a little bit higher than 12 because some of those atoms are actually carbon 13, not carbon 12. So there's a very simple mathematical way that we will learn in another video of how to calculate average atomic mass. It's a formula. And in order to know that formula, or I shouldn't say in order to know that formula, in order to use that formula, we need to know natural percent abundance. And how do we know what is the percent abundance of the different isotopes? How do I know that 99% of all the oxygen in the world is oxygen 16, but there are some other isotopes, but they're very, very rare? I know that through a process that's called mass spectroscopy. It's an analytical technique, and in order to go through or to learn this technique and how we can figure that out, we're going to work through something called a POGL, where we're going to sort of figure that out together. We're going to do this activity in class together. So the next few pages talking about mass spectroscopy. Feel free to preview it if you would like, but we're going to work on these in class either in small groups or as one big group.